okay. You're okay. I'll help you out. Oh, hey, good to see you there. My name's Lucas Canty. I'm a member of Team 64, aka the CAM-DAR is Life System. The problem that we see in hospitals across the country are patients not receiving care in time because they are misproperly diagnosed inside of their care facility, potentially having fatalities or worsening injuries inside the waiting room of the hospital they want to receive care at. Our system aims to address this issue by using a world-class computer vision and machine learning algorithm to look at the patient's posture and address whether they're in a compromised position. Following that, we use our aimable radar system to take their vital signs and alert emergency responders if we see fit. Let me take you on a tour.
Our cameras are set up on tripods in corners of the room. This gives us the ability to see the entire space and ensure we have full room coverage. Between the two cameras, we have a millimeter wave radar sitting on an altitude azimuth mount. Currently, our system sits on tripods, which we're using to mimic being mounted on the ceiling as it would in a production environment. Able tags help to define our working environment by setting hard boundaries for accurate detection, working with depth, and navigating occlusion. Additionally, working within a defined space allows us to direct the radar with better accuracy. The cameras go through an initial calibration process with the tags upon setup in the new environment. Once calibration is complete and checks have been done for both radar and mount, the system is ready to roll. The two corner cameras feed live videos to our Jetson, which we use as our main processing unit. Images are decoded and run through our computer vision model, which analyzes body posture to determine health status. We're looking for medically compromised individuals, which trigger a detection. This then sends a signal to our altitude azimuth mount, which directs our radar to begin taking vitals. Our computer vision model consists of 12 components used to break down our live video feed and analyze body posture. As of today, we're capable of analyzing 5 different body postures and 2 emergency states for heart attacks and choking. We're also performing motion analysis over time so we can differentiate whether someone has fallen down or decided to lie down for a quick nap. This is done through an algorithm modeled after a transformer. The model is capable of unique identification through room placement and allows us to keep track of the person's movement so long they're in frame.
Before the Jetson or computer vision model sends the 3D coordinates of a compromised individual, the information first must be transformed into the radar subsystem's body frame. This is done to make sure the line of sight to the target coordinates and associated angles are relative to the radar's orientation. Once this is done, the degrees of rotation in altitude and azimuth are calculated for the relative coordinate to align the radar properly. The radar subsystem itself contains its own centralized power supply, taking in outlet AC voltage and converting it to usable DC voltage for the Raspberry Pi, stepper motors, and the radar. The Raspberry Pi is the computer of the radar subsystem, directing the motors and processing the radar data. Upon initialization of the subsystem, the Pi ensures the radar is set to a known home position via limit switches by rotating the azimuth and altitude stepper motors simultaneously. After this, a socket is opened to talk to the Jetson, and the rotation angles calculated previously are received and converted to the correct direction and number of motor steps required. These steps are then threaded to the motors such that simultaneous rotation and alignment of the radar with the target occurs. The radar itself is then initialized to take measurements, and upon finishing radar analysis, the motors again return to home position, awaiting new orders.
We use a millimeter wave radar that emits a series of linear chirps whose return is mixed with the original signal. Over the short time frame within one chirp, this gives us the range of the target, and over the longer time frames between multiple chirps, we can measure the thoracic motion of the target using just the phase information of the radar.
To summarize, the CAM-DAR system bridges a critical gap in modern healthcare by enabling the continuous monitoring of patients in low acuity areas such as waiting rooms and clinics. By integrating a multi-camera computer vision pipeline with a millimeter wave radar, we have created an autonomous, non-contact system capable of alerting first responders to visual health compromises and abnormal vital signs. In a practical application, this early detection allows clinicians to initiate time-critical interventions faster, ultimately saving lives.